Thank you everyone for joining this session. My name is Marco Marini. I'm Chief of the Data Governance Division in the IMF, the International Monetary Fund, and also I'm the head of the Big Data Center, which is a new thing that we started this year. I'm delighted to chair this session. This is a session for the compilation of economic indicators using AI and data science. Of course, this is important for IMF. It's a core business on IMF. So I'm really looking forward to hearing, the presentations, the use cases that will be presented today. So we have 5 very interesting presentations. We give each presenter has about like 12 minutes to present, and then we will spend maybe a couple of minutes to see if there's any Q&A from the audience. You can put your questions in the chat, and then at the end of the presentation, I will take them. And for the speakers, I'll give you a thumb up sign in Teams when you have perhaps 2 minutes left. So my job here is really to make sure that we finish on time. We have to go back to the main room at 9:20, and we will also take a break around 8:40 for 10 minutes. So we are just gonna take a pause from this long meeting, and so I'll monitor the time and let you know when we have this break. So without further ado, I would give the floor to our first presentation from Abel Coronato Irogas. I hope I pronounced that well. Abel is Deputy Director of Research in Data Science at INEGI, Mexico, and he's going to present on the Earth observations and machine learning for estimating agricultural activity. Abel, over to you.
Perfect. Okay, thank you very much. Good morning. I'm happy to share the progress of our supervised crop classification project. This project is part of the annual research program of INEGI. The program is made with ideas and suggestions from all the parts of the institution. This project was proposed by a regional directorate, which shows how our national structure is involved in choosing research project priorities. And we have working on this project for only 9 months out of the 24 months. So we have completed a little over 1/3 of the time. And today, we share some of the initial results. Okay, maybe as you know, as part of our responsibilities at INEGI, we produce the statistical and geographical information that Mexico needs to support decision-making and public policies. And remote sensing is very important tool for studying natural resources and the environment. It has many applications, and agricultural monitoring is one of the key ones. New technological advancements give us a great opportunity to generate better information. Therefore, we are adopting these innovations to improve our processes. With the experience we gained from the events like the 2022 agricultural census, we applied several techniques. We identified cultivated and uncultivated areas. We determined irrigated agricultural zones. We studied the condition agricultural areas at different stages, and we also identified crops. This work helped us to find opportunities to support activities that focus on better using these technologies to generate information from the agricultural sector. Our main objectives are, we want to define a method to analyze agricultural activity using cloud processing of satellite images. We aim to detect agricultural activity by studying changes in vegetation indices over the time from satellite images. We plan to identify areas that use irrigation by analyzing vegetation indices over times. We intend to identify important crops and estimate the areas to validate and compare with historical data. Since this is a research project, we understand that some objectives may be possible while others might need to be adjusted. And the first phase, we have decided to focus on identifying crops within the agricultural frontier. By concentrating on this area, we hope to build a strong base for our method. As we continue, we will learn more about what we can achieve and adjust our goals accordingly. I would like to clarify that the next 3 slides represent the experience of the General Directorate of Economic Statistics, or DGEE, which coordinates agricultural census at INEGI. These slides provide institutional background that aligns with the research proposed by the Regional Directorate, reflecting what has been done and what hasn't in past exercises. The DGEE conducted various exercises in crop identification using satellite images. The general methodology involved several steps. First, they obtained satellite images that covered the area of interest and matched the main crop season. Next, they identified specific points where the planted crops were known. Using supervised classification techniques, they combined the satellite images with field data to estimate the coverage of each previous identified crop with the images. They applied this methodology to various crops and regions across the country, including agave, alfalfa, broccoli, sweet potato, asparagus, corn, sorghum, covering thousands of hectares in each case. Um, uh, they had two stages of experience. Stage one, 2013 to 2016, they used purchased satellite images with 6.5 meter resolution and commercial software. They collected high quality field samples by visiting selected areas, and they achieved good definition and positive results for some crops. The stage two, 2018 to 2020, they use free satellite images like Sentinel-2 with 10-meter resolution and open source software. They obtain field samples from administrative agricultural records and validated them in the office. Even with limited data, they still achieve good definition and positive results for some crops. This approach was cost effective because they use free images and open source software. Finally, they have not used certain data and techniques yet. They haven't used time series of satellite images, which could help track changes over time. They haven't used radar images like Sentinel-1, which can see through clouds. They don't use image segmentation techniques to divide images into meaningful regions. They also haven't included additional data layers like digital elevation models, climate data, or spectral indices. Finally, they don't use geomedian composites, which are cloud-free images made from several images over time. These are areas they could explore in this research project. Between 2021 and 2023, our team, in collaboration with DGEE, our team is the team of the Data Science Laboratory at INEGI. We mapped the agricultural frontier. We use satellite images from Landsat and Sentinel-2 to distinguish between cultivated and not cultivated land, comparing our results with the 2016 Agricultural and Livestock Survey. By refining our methods, we improved our classification accuracy using Sentinel-2 data from 2019. We achieved a 91% accuracy, better than earlier results with Landsat data. These positive results show our approach works well in distinguishing cultivated land. Now we are focusing on classifying specific crops within the areas using the tools and methods we have developed. Now I'd like to share with you the progress we have made in our research project in 2024. We conducted a comprehensive literature review on crop identification and mapping using satellite images. We studied various techniques and strategies. Our review showed that many researchers use time series of image satellites, combining optical and radar data like Sentinel-1. They apply supervised classification techniques such as random forest, deep learning methods. These findings help us to decide our approach. We plan to detect and classify crops using satellite images, Landsat, Sentinel-1, Sentinel-2, and Landsat. The ground data like crop calendars and field data. We process this data to create cloud-free images, segment them, and combine data from different sensors. We will extract features like vegetation indices, study textures, include spatial and climate variables, and create time series. We will use supervised machine learning methods like neural networks and deep learning, optimizing them with auto machine learning. We will evaluate our models using metrics like confusion matrices and F1 score. Our goal is to produce useful agricultural products like crop maps and yield estimates. This plan will guide our research and help us to adjust our goals as we learn more. We have set up a test environment or sandbox for our project. This is a powerful cluster of 160 CPUs, 1.5 terabytes of RAM, and 16 terabytes of storage. This environment is for pre-production and training. We use Jupyter Hub with Python so our team can work together easily. We manage our container with Docker Swarm, and we run Python on Ubuntu. We have a great storage rate that functions like as a data lake, and we have 45 terabytes of network attached storage. All of this is on premises, which means is hosted locally. This gives us a better control over the data and the processing capabilities. So our test environment uses Jupyter Hub, which allows multiple users to access the system. Team members can log using their institutional email and password. Our team includes people from different areas: fieldwork specialists, geomatics experts, biologists, agronomists, physicists, and data scientists, of course. We all work together as a collaborative environment. We use Python for work, so it's important for our team members to have programming skills. We are working on improving our Python skills as a team. And we, after that, we implement the first ideas of methodology in Python. We studied the Yaqui Valley in Sonora during the autumn winter season, 2018 to 2019. Our input data included the area. We focused on the level data from the DGEE, which we got from administrative records. We use satellite data from Google Earth Engine in Python, including Sentinel-2, Sentinel-1, and Landsat. In processing data, we took advantage of Google Earth Engine power in Python to perform image fusion and create mosaics, as well as to calculate spectral indices. We made combined optical mosaics from Landsat and Sentinel. And also, we make radar mosaics with radar vegetation index already calculated. By doing all this processing in Google Earth Engine, we were able to download the images that were already processed and ready to use to complete with all the spectral index data in the image. After obtaining these ready-to-use mosaics, we perform object-based segmentation to divide the images into meaningful regions. We then extracted features based on vegetation indices and bands by calculating statistical characteristics like mean, standard deviation, etc. Each polygon created from the segmentation was the object we studied. We applied machine learning methods, including auto machine learning models, random forest, stacking methods with extra trees, and multi-layer perceptrons. We evaluated the accuracy of our models using global evaluation metrics and confusion matrix. And we have this result. We create a tutorial in Jupyter Notebook. This tutorial guides users through the process of crop classification in Python. And the tutorial serves as a baseline of our methodology and helps the team members learn and contribute. To make our work more useful to users outside of INEGI, we are building the tutorial in English, and we are with local functionality. We have developed a tutorial for setting up the environment for crop classification in Python, integrated with Google Earth Engine. This tutorial guides users through the installation process using Miniforge for easy Python and library management. It includes code examples and instructions to help users to set up the environment and run the analysis, while the servers. It serves as a baseline. It can be a good starting point for anyone who wants to be working on this kind of exercises. We plan to publish the complete tutorial in the joint task team on the use of Earth observation and data agricultural statistics. Finally, we think have good enough results. We plan, of course, to incorporate additional features and data to improve our models. The next steps are to strengthen our skills in data science. We will continue our experiments and optimize the methodology as a team, and we plan to expand our study areas to more regions, adapting our methods and each context. We also want to broaden our analysis to more crops and seasons. By doing this, we can improve our models and provide better information. Finally, To summarize, this crop classification project is the result of a strong collaboration between the General Directorate of Economic Statistics, DGEE, the Regional Directorate of North Central Region, and the INEGI Research Area. By working together, we have used open data sources and cloud technology to improve our efficiency. And while our preliminary results are encouraging, they are also highlight areas we can improve. This project emphasizes the importance of the teamwork and continuous skill development. We will continue to refine our methods, advance our methodologies, and provide valuable information to support agricultural planning and decision making. Thank you very much.
Thank you, Abel. This is excellent work, and thank you also for being on time. I know that we are already sort of running late, and unless there are like urgent questions, I mean, I encourage everyone to use the chat to ask questions, and maybe Abel can also take these questions in the chat. And if we have some time left, perhaps later, we can see if there are questions for all the other presentations. So with that, I would now, again, thank you very much, Abel. I will now move to the next presentation. Next presentation is from Gert Buiten. I hope I pronounced your last name. I think
it's well enough.
Yes, well enough. That's good. He's from Statistics Netherlands, and he's going to present work which I think was mentioned by Francesca earlier today on AI/ML for estimating firm-level supply chain network. Over to you, Gert. Thank you.
Yeah, well, thank you very much for this the opportunity to present our work here. As you indeed said, I'm working at Statistics Netherlands, but I'm giving this presentation as the work package leader of the work package in the AI/ML for official statistics project that Frankie already mentioned in the introduction session. In this case, this work package, we want to use machine learning to estimate firm-level supply chain networks. Let's first start with something about supply chain networks. I think the last few years we have all become aware of the importance of supply chain networks, where you can see that, for instance, if only one ship blocks the Suez Canal, then the entire world economy runs into problems, because these kind of shocks tend to propagate through the network, the production network all over the world, and for instance lead to empty shelves in supermarkets. And this propagation of shocks is something that has to do with network effects in the production networks. And since they are sometimes very important, it's a very important research area also by policy researchers, for instance, to see where are the weak spots, the vulnerabilities in a particular production network or a particular supply chain, but also how can you make supply chains more resilient to potential shocks. And for instance, in the bottom image here, all these containers underwater, I think there are more and more problems all over the world with floodings due to climate change. This is also an area that you really want to know where are the weak spots in terms of climate risks. That also means that we could use this kind of data and this kind of, let's say, science to investigate the possibility of using the network effects in a more positive way, for instance, for the energy transition or for increasing the sustainability of supply chains, using the network effects in a positive way. What if an important supplier at the beginning of a supply chain does something which makes his or her firm more sustainable and less dependent on fossil carbon fuels? This would have an effect all through the supply chain. So those are two major areas of interest regarding supply chains. For that, you will need really good data. So supply chain networks matter, but also the data matter. This brings me to the next slide. The key drivers for this work package in the AI/ML for OS project. Supply chains are very important, but if you look around the world, there are some countries that have very rich data and very good data sets, including practically all the firms within their country. But a lot of other countries do not have such kind of data. And from the data that we have been analyzed around the world from the countries that have the good data, we see that there are, if you look at the structural uh, part of the networks, the structure of it, you see that there are a number of generalities that you can see popping up in all these networks, which means that there are some structural how do you call this, similarities that you can use to use information from one country also to estimate a network in another country. And this is exactly what we want to do. A number of the EU member states have very rich data sets, others do not. And what we want to do is to use the data from countries that have good data sets to help others to create data sets that are model-based, but that are fit for purpose. And one of the most important approaches for this is, of course, machine learning. And on the next slide, you can see the approach that we use more or less as a backbone of our project. In Portugal, Statistics Portugal has a very rich data set of administrative data from the tax authorities. We want to use that to develop a firm level network data set, including basically all the firms in the country. From that network data set, we want to derive a training set, a test set, and validation sets. We want to develop models that we can train on these data sets using machine learning. And those models are supposed to be able to estimate whether two companies have a buyer-supplier relationship, a buyer-supplier link. From data that is available at all the national statistical institutes, at least in the European Union. And in doing that, we want to build on work that has already been done at Oxford University. They published a paper about a year and a half ago on using machine learning to do exactly this. And their results were quite promising, but for a large extent, they had to work with commercial data sets that, for instance, only have the most important companies in a country. So what we want to do is use their data, their modeling approach, and make it more generic and apply it to other countries. Once we have trained our own models, we want to apply these reconstruction models also to other countries within the project, but also potentially countries outside of our project team, to see how do they perform. Are they indeed well enough general applicable also for other countries? Are there things that we can improve in the models or in the software, etc.? And this will be, let's say, an iterative process for about a year. Parallel to that, we also wanted to develop methods to add weights to the estimated links. And finally, of course, we want to make the resulting software available to other member states and other national statistical institutes in a way that they can really use them themselves. On the next slide, I put some additional points for attention in the modeling process. The model should at least include NACE codes, so the industry activity of the firms. It should contain their geographical position, and it should have some kind of indication on their firm size, because from the networks data that has been studied, we can see that some NACE codes combinations have a very, very high chance of having buyer-supplier relationships, whereas other NACE code combinations of NACE codes are much less likely to have a link. Also, if a firm can choose between two suppliers and one is quite close by and the other one is very far away, they tend to choose the one that is closest by. So that's why geographical distance is important. And also large firms, large users tend to link with large suppliers. That's also one of these stylized facts that comes out of these analyses. This is basically the approach that is used also in the modeling approach from the Oxford University. Further, what we want to do is feature engineering in such a way that we can apply these models at least to all the EU countries. And of course, we have small and large countries. And for instance, in Portugal or in the Netherlands, the geographical size or the geographical distance is much shorter, so to speak, than, for instance, in France or in Germany. The same also accounts for the size distribution of firms. So we need some kind of good normalization to make these models well enough to apply in all member states. Also, we have to find the best way to deal with the fact that buyer-supplier links are what they call rare events. Less than 1% of the potential buyer-supplier links actually exists. So any model that you just simply train will predict that there is no relationship at all. There are techniques for that, and we'll have to find out which one works best in this case. And of course, we need to create robust coding pipelines for the software and to develop a number of adequate quality indicators to assess the quality of the models that we have, and we apply them to various countries. And you need the quality indicators also to see in which areas or which aspects the models need to be improved. On the next slide, this is the Work Package 11 team. There are representatives from 4 national statistical institutes in the EU, from Portugal, Poland, Netherlands, and from Ireland. 2 universities are involved. Glenn Margeman from the Free University of Brussels, who has been very important in developing the Belgian network data set based on administrative data, and he is transferring his knowledge, so to speak, now to the people in Portugal. And François Lafont from Oxford University, who is one of the developers of the model and the approach that we have just been discussing. They also provided us with the basics of their software, etc. And finally, last but not least, Eurostat. They are not only one of the main funders of this project, but they are also looking into our progress and seeing probably a little bit further down in the project, also to see how policy applications and policy analysis at Eurostat and at the European Commission could already been done with the data sets that we are busy developing. Finally, on the next slide, this is the overall schedule of, let's say, our official deadlines when we have to deliver things to Eurostat. At the end of the first quarter of next year, we want to have the training sets and the test sets from Portugal. We already have from them a synthetic data set that we can use for, let's say, technical testing and developing software, etc. The final models on the binary link, so whether there is a supplier user link or not, should be ready by mid-2026. That's quite a long while in the future. But in the meantime, we probably will also have intermediate results that we can share, at least with countries that want to help us try out our models. Maybe we'll publish things in other ways as well. We'll have to decide on that. We have to deliver a report on these binary networks early 2027. In parallel to that, we'll work on adding weights to the networks. The final report of that will be available at mid-27. And finally, the publication and dissemination of all the project results will be early 2028. But as I said, intermediate results will be available earlier. And also, if there are any people in the audience that say, well, at our statistical office, we would also help you to try and test your models, you're more than welcome. So please get in touch with us. And I think this was my last slide for my presentation. So thank you for your attention. And if there are any questions, I'll be happy to take them.
Thank you. Thank you very much, Gert. This is very promising work. Supply chains are so important from economic perspective, and I think the fact that you said these models can be applied in all European Union countries and hopefully beyond. I think that's very promising for and everyone in the call that are interested in using this model. So yeah, we definitely encourage anyone interested in this work perhaps to put questions, comments in the chat for Gert, and Gert can perhaps react to that. Yeah, thank you very much, Gert. So we're doing good in terms of time. So we have our next presenter, Christian Stefan. from Statistics Austria. Is Christian in the call? I think.
Here? Can you
yes,
hear me?
Yes, yes.
Okay, thanks, Marco. I'm trying to share my screen now.
Good. Okay, so
give me a
Christian will
second.
present on solar panel detection using orthoimagery and deep learning. So again, Christian, you'll have about 12 minutes, and just a reminder for everyone: at the end of Christian's presentation, we will take a 10-minute break. So Christian, over to you, and then we'll resume after your presentation ends. Thank you.
Thank you very much, Marco. Just can you assure that you can see my presentation screen? Because then I could start with the presentation. Perfect.
Yes.
Okay. Okay, ladies and gentlemen, I'm going to give you a brief summary of a research project that Statistics Austria is currently conducting with the support of Eurostat. The GEOS project, which is an acronym for Geospatial Statistics for Energy and Environment, started in March this year and aims at identifying solar panels and buildings using autoimagery and deep learning. So what are the topics we will cover here in brief? I will start with explaining why this project is so important for geodata production. And next, I will introduce the database that is the autoimageries we use as ground truth and the deep learning model we are currently investigating within this project. And finally, I will briefly explain to you the methodology and technical aspects and what our next steps are in the project. So as you all know, climate change is happening, and it's forcing society to invest billions and billions of dollars in the energy transformation, that is from fossil fuels to sustainable energy. And in order to know where future investments will be most efficient, there's a growing need for better and more timely data, especially georeference data and cartographic display of solar panels. And in Austria, we have currently 2 governmental organizations collecting such data. And the first one is the Climate and Energy Fund, which provides subsidies to households and companies for the installation of new solar panels on buildings and open spaces. And the second one is called Clearing and Settlement Agency for Green Electricity, ÖMAG, which plays a central role in the processing and implementation of public subsidies for renewable energy. However, these data do not contain all relevant information, which is due to the fact that very small systems known as Berkeley solar plants in Austria do not receive any funding at all. And secondly, there is also a lack of spatial detail, as the data is provided at the level of the local administrative units, which is in Austria the municipality level. And therefore the available data is not geolocated, which is really, really bad, and provides only a rough understanding of the spatial distribution of solar installations here in Austria. And as you can see on this map, you can already get a rough idea where the most solar panels are installed in this country at the community level, but no localization is currently possible, and that's where this project kicks in and tries to develop solutions. So we have 2 issues. On the one hand side, we are seeing an increasing popularity of solar panels among the general population due to massive public support. Here in Austria, subsidies can reach up to 50% of the investment costs, and also a wide range of different applications. As you can see on the right-hand side, there are different types of solar panels, ranging from solar farms, open space solar plants, rooftop solar systems, and balcony solar systems. And another potential data source we were investigating during the initial stages of the GEOS project is the so-called Certificate of Origin Database, COODB, which is managed by E-Control. This is a governmental agency which acts as an electricity and gas regulator here in Austria, and each Austrian citizen who installs any type of solar system has to notify E-Control of its purpose. And but unfortunately, due to data protection issues, a cooperation between Statistic Austria and eControl was not possible. And this is where GRS and remote sensing kicks in. In recent years, I guess not only here in Austria, but also all over Europe, there has been a paradigm shift towards Earth observation data for statistical data production and analysis. And as there is no homogeneous data sets on a national level available, we at Statistics Austria decided to evaluate the feasibility of using high-resolution autoimagery and deep learning models to detect solar panels on building roofs. What kind of databases are we using? We are using autoimagery. I guess, as you all know, an orthophoto is an aerial or satellite image that has been geometrically corrected, so it's auto-rectified, and it's so that it follows a map projection and can be used to measure areas and distances. And the digital autoimagery of Austria is available in RGB, a red, green, blue, or CIR, color infrared, with a spatial resolution of 0.2 meters. And each year, new flight covers approximately 30% of the Austrian territory, so that the national coverage of the resulting autoimageries is updated every 3 years. And what you can see on this slide is also the test region we used to test the pre-trained deep learning model, which I'm going to explain in the next 2 slides. So before that, what are the benefits of using digital orthophotos? First of all, it's a new data source that can be used to enhance existing statistical information with additional data, in this case, geospatial information. And data objectivity and consistency means that data is collected consistently over time and geography, which is the fundamental for training and adapting AI models. Spatial explicitness refers in this case to the precise and direct representation of spatial information, meaning that each piece of data is explicitly associated with a specific location on the Earth's surface. Quantifiable data, meaning that orthophotos can contain measurable and spatial accurate information that can be used for analysis and calculations within a GIS. And last but not least, the data availability. It's a bit of a limitation here that the Austrian digital orthophotos are currently updated only every 3 years. Also, there are plans for shorter cycles in the future, but the data are available and can even be obtained at little or no costs on the requirements. And that was also one of the reasons why we wanted to build our, let's say, research purpose on the autoimages available here in Austria. But where there are advantages, there are also limitations. So what are our experiences with that? First, the timestamp of the detected solar panels from the autoimages depends logically on the timestamp of the orthophoto. So there is no real-time data. So there's no real-time data can be generated and detected. And second, autoimagery requires a lot of storage space. And at the moment, there are not enough resources available to store the data for the whole area of Austria, but alternatives such as computing time slots for each area or hosting and computing externally are currently investigated here at Statistics Austria. And thirdly, vertically mounted solar panels, for example, on building walls and balconies, can not be identified using orthophotos. So in order to use the deep learning models for solar panel detection, we tested a pre-trained model provided by Esri, the software company responsible for ArcGIS Pro and ArcMap. And the model was trained on US data and had an average precision score of 0.764, which is quite high. In contrast, a 100% detection rate would amount to a precision score of 1.0. And another advantage of the pre-trained model was that it can be readily implemented using Esri's own ArcGIS software by implying an implemented object detection algorithm. And hence, there was no need to purchase new software to work with. And the model that was used is the mask-R-CNN algorithm, which stands for mask region-based convolutional neural networks. So what does it do? The algorithm scans the input orthophoto and suggests a set of bounding boxes around potential objects, hence reducing the amount of data that needs further processing. And this is called object detection. And based on the object detected, the task of semantic segmentation is to classify each pixel in an image into a category or class based on its content. And the object instance segmentation, which is basically the core of the mask-RCNN model, is a recent approach that includes both object detection and semantic segmentation at once. So what are our initial results? We applied the pre-trained S3 model to a test site in Austria, as I have shown you before, where there are many single-family homes with solar panels on the roof. So that was a precondition in order to choose this test region. And the implementation was quite straightforward, but we saw earlier on the model that the model performed very poorly with Austrian orthophotos. Meaning that the pre-trained model does not transfer very well from the US to Austrian locations where data and land use structures are quite different. And another major problem which we realized is that the model requires suitable orthophotos as input, so 5 to 15 centimeters spatial resolution. And there's only one region in Austria that produces auto imagery of that resolution. And most areas in Austria are covered with 0.2 meter auto imageries. And therefore, the pre-trained models is not well transferable at the time to the available data and requires retraining. But retraining requires ground truth data, which must be generated in advance. So to sum up, we need to make some methodology improvements to our processing pipeline, which we have already planned and are starting to implement. Concerning the orthophotos, we're using Viennese DOPs, which have a higher resolution and offer good results for creating a reliable data set. We also need additional data, especially building footprints, to exclude misclassifications like cars, for example. And we also want to test if orthophotos in the near infrared spectrum could provide better results in comparison to RGB. And the ultimate objective is to create a robust Austrian training data set, which can also be used at low resolution for calculating the solar plants on the whole Austrian area. So what are our next steps? We are now working to implement the described workflow and further evaluate the results. Furthermore, we intend to establish contacts with other Austrian fellow states and other stakeholders to assess other potential data sources. And thanks to Eurostat, we have also a good network to other EU-related projects in national statistic institutes and intend to evaluate other solutions and models. And if the proof of concept is successful, then a large-scale processing would be our next objective. But this requires, I guess, additional infrastructure and funding, but we are not there yet. And this closes my presentation.
Thank you very much, Christian. I think this is also joint work with Nina. I know that Nina was unable to present today, and thank you very much for presenting this very, very useful. And I like that you're talking about proof of concept, and then scaling up is another issue, right? So it's takes some more efforts to get there. So I suggest that now we break for a quick break. So it's like 8:44 in Washington, D.C. So why don't we take perhaps 6 minutes so we can rejoin at 50, so in 6 minutes, and then we will start with the next presentation by Adi Susanto. So it's a short break, but let's just do whatever you want. And so we'll rejoin in 6 minutes. Okay. Thank you. You can stay in the call, please. Okay. Welcome back, everyone. So we can resume. We have about 30 minutes before this session ends, and we have 2 more presentations. So I'd like to now call Adi Susanto from Statistics Indonesia. Is Adi in the call?
Yes, Marco.
Hi, Adi. Okay, yes. So he is going to present AI and ML for estimating economic indicators. So Adi, I believe you can share your screen presentation.
Yeah. Okay.
Yeah, now I can see you.
Sorry, Marco. I think I have problem in
Sharing
the presentation. I think I already sent the link.
I can
Let me
present for you
share
if
it with
you wish.
everybody.
Oh yeah, thank you, Lee. This is a
Just
sudden problem. So sorry for that.
Just a minute, a second.
we can help. Thank you. Thank you, Maria.
Okay.
Okay, we can see the
yeah.
presentation. Yeah, just say next when
Okay.
you need to move the slides. Thank you.
Yeah, sorry for that. Thank you for handing me over the mic, Marco. And I think this is not in the present. Okay, yeah. And we are going to discuss in this case about the potentials of AI and ML for estimating the economic indicators. But first of all, I would like to disclaim that as I'm part of the UN Network of Economic Statisticians, this will be from the perspective of user, which is the economic statistics. Okay, can we go to the next slide? Yeah, okay. Next. Yeah, as we know that in current landscape of the economic statistics, the data, the business of data, starting from the data collection, data processing, data analysis, and so on, are getting bigger challenge due to the digitalization and globalization. And lucky for us that at the critical time, we have potential powerful new tool to give the light in for the effort of providing insightful economic insight. Okay, next. Regarding the application of AI and machine learning in time series forecasting, my team in national accounts already collect some research and studies and also practices that can be used as reference to learn or to implement the AI and ML. Like in this case, we have a good reference if we want to apply the AI and ML in GDP growth or inflation or in unemployment rate forecasting because it's already there. And by using the various method and models of AI and ML, we can have a better result. Like in this case, the error can be reduced and also better sensitivity on the prediction and also better timeliness in terms of better frequency and also earlier results of the estimation. In this case, the model that we choose depend on the data inputs that we use. Then next, still in the umbrella of time series forecasting as the soul of the economic statistics, is not limited to the GDP and inflation and unemployment, but we can see also that trade flow analysis also able to be improved by using the AI and ML technique. And also the consumer spending can be reduce its error until 25% by using the technique. This technique is a combination between the traditional time series model, but then enhanced by the graph neural network. With graph neural network, we can have the perspective of common time series with the visual pattern. And also, there is also effort by the Bank of Japan to make the production industrial index with better accuracy. Next, please. And now casting as the new toy of the economic statistician to provide the second opinion of the estimate are now can be enhanced by using the AI and ML. It's done by the, for example, for GDP nowcasting, the New York Federal Reserve already done the study by using the dynamic factor model that have the result of earlier release until 6 to 8 weeks before the official release. And also, other thing that we can pick up here is the frequency of the estimate can be made better, like the monthly official statistics can be detailed into daily estimates. And then next, please. Still in the umbrella of nowcasting, there are also some examples of studies done by the Bank of Korea, Bank of Japan, and the World Bank. And most of the studies here use the AI and ML technique, which are suitable for the data input. Like, for example, if the data input is a type of data which is not sequence data, the CNN or convolutional neural network hybrid will be used. But if the data is in the type of sequential data, the other model, which is RNN, will be used. So that depends highly on the data that we use. Then next. And about big data, the problem with big data is that the amount of data that we have to compile. And the solution has potentially come from the AI and ML, because the AI and ML model are able to proceed faster than the conventional model. Like in this case, the ONS UK use several models because they use a lot of variety of data source. So the models are the combination model. The result, we can see that the coverage can be expanded from 100,000 price point daily to 1 million price point daily. So it's more or less 10 times. And also about the amount of data, we can see in the USBLS, they have to compile 30 million monthly of online job posting. That we know that it's in the various form of text, and then they are able to measure with improvement the significant increase of speed. And WTO also did the same by having the better accuracy and also reducing processing time significantly. Next, please. Still in big data, sometimes we can see that the effort done by using the ML is for a specific concern. Like in this case, the Eurostat, the consumer behavior analysis, they want to have a better results of the analysis, but also keep the privacy preservation. So they use all of the AI models that are able to keep the privacy preserving analysis. Next, please. But like two sides of the coin, there are also issues in implementing the AI and ML from the perspective of economic statistics. The first one is the data quality and bias issues. As we know that some AI models are highly dependent on the quality of the data training, and also lack of transparency and interpretability. So some researchers say that many AI ML models are black box because we cannot see the process inside it. And also there is a issue of over-reliance on AI ML model because of tend to overlook the human expertise. There is also privacy issues. We already heard that in previous presentation. And next. Besides, there is also ethical consideration that has to be concerned here, because some AI ML model have potential to be biased because of political or economic interest. Technical challenges are also issues because not all economy have the same capacity in terms of human resources and in other computational resources. And the last but not least is regulatory and standardization issues, because we know that we are still lacking of global standards for AI ML that we use in economic forecasting. So the result of our forecasting is possibly to be not standardized. And next. As the wrapping up, we know that in the implementation of AI and machine learning, there are lots of benefits as well as also challenges that we have to concern. In this case, we have some needs, which is to collaborate among statistics producers in providing data or harvested data, providing knowledge and also other resources to be able to have good AI/ML models to be implemented. And also it is necessary to understand the decision-making process of AI and ML. So the model will be more interpretable and also accountable. Last thing is to highlight the ethical implications of using AI/ML in economic analysis, because it will be the base for our effort to produce the economic statistics. Okay, next. Yeah, that's all for me. Thank you very much for your attention, and back to you, Marco.
Thank you. Thank you. Thank you very much. I think this was a very helpful review, Ari. If available, maybe it would be good to have also links to if these are published papers. I see the presentations, know that all this work done by all these organizations. Maybe if there is a way to put like maybe the list of links in the end where we can provide also reference to these research works. I think that would be helpful, because you really made a good review, Ari.
Thank you.
Yeah. If there's any question, I guess I'll encourage everyone to use the chat, and Ari can respond there. So I will move now to the final presentation from Ike Maduaco. Ike is from MF, is from my team. Ike will present there's a question. Maybe I suggest that we take this question later. So as you said, and maybe we can have maybe a few minutes for questions from the floor, if you don't mind, Hassan. So let's move on to the next presentation. And so again, this is from Ike. Presentation is on nowcasting. Adi mentioned nowcasting a few times. So we'll see what we are doing on nowcasting at the IMF. So Ike, please, over to you.
Okay, thanks, Marco. Can you see my screen?
Yes, we can see you.
Okay, perfect. Let me project it. Okay, thanks everyone. So my presentation is on, as Marco mentioned, on how we are shedding light on economic activities in many countries of our membership, using satellite data and of course machine learning. And this is the case for GDP nowcasting, and Hadi has already, covered some of the preamble. But the major motivation for this work for us is the constant need for the IMF to assess economic conditions in many countries of our membership for many policy advisory reasons. And to do this, we are constantly faced with a lack of timely and granular data. And for some countries where there are some macroeconomic indicators available, they often do not come in high frequency as needed, and there are always gaps. I use this as an example, actually. So these country groupings, and this is not just particular about this region, is a problem that cuts across different regions in the global south and some part of global north. Here you have countries in Group A where there is some quarterly GDP data that we can train models on. There are some macroeconomic indicators as well that come in high frequency. However, countries in Group B, you have quarterly GDP data, but there are no available macroeconomic indicators that are openly available that we can assess at high frequency that we need to train models on it. And it becomes much more difficult for countries in Group C, where there are no quarterly GDP data. The best you can get is annual GDP data, and there are no indicators to develop models. But our interest is on how we can build a framework that is inclusive of all these countries, irrespective of their data problems and data situations. And therefore, we have to resort to alternative, indicators, what we call non-traditional indicators. And one of the major sources of non-traditional indicators is satellite data. And the two major, advantages of satellite data for us, one is there is global coverage, and it often comes in high frequency. But the problem here, to start with, is what satellite indicators, do we choose, or do we, rely on? We started on with nightlight, and because there have been many studies that show that nightlight can be a good proxy for economic activities in different countries. And our internal studies, like you see on the screen, also show that nightlight can move in the same direction, or have high correlation with economic activities and GDP, and including the many studies from the World Bank. And therefore, nightlight was an indicator that we had to plug into the model to see how it behaves. Another indicator we looked at was NO2. NO2 is one of those aerosols that, for example, you have CO2, you have SO2, but NO2 particular for us, it stays in place from where it's produced, right, on the top of the atmosphere. So and there have been many studies that show that NO2 can be a good proxy for economic activities, especially in manufacturing and industry where there is a lot of combustion. And our internal studies as well show that that NO2 can, this is an example for Uganda, that NO2 moving in the same direction or has high correlation with economic activities in Uganda. And the recent studies from the World Bank, you can see that NO2 was able, even doing better than nightlight, to capture the cyclical component of the world economy. You could see the depression captured by the NO2, the depression caused by the financial crisis in 2008, and the pandemic in 2020. So for us, NO2 was an indicator that we also wanted to plug into the model. To be able to capture the agricultural sector, because we are aware that for many countries, agriculture is the mainstay for the economy, and there is need to capture that sector as well. And then to look at something that is global, that has global coverage, we looked at vegetation indices. And the first vegetation index we looked at is NDVI, which many studies have shown that NDVI can be a very good proxy for agricultural activities. And the second one is EVI, which is similar to NDVI, but is soil adjusted, a little bit different from NDVI. So in a nutshell, our methodology in a nutshell is, for example, countries in Group B where there are no indicators. So our hypothesis is it possible to use satellite indicators alone to be able to develop some machine learning model or GDP nowcasting model to a very good accuracy that is reliable? And the answer from our results is yes. And so the methodology in a nutshell you see on the screen is an end-to-end pipeline where we stream data from different sources, satellite indicators, and then we crunch the data using different machine learning model, actually lots of different machine learning model like you see, and then we select the top performing models and as the final model. The results quickly, I'll show you just a few examples. This is for Uganda, and you see this is just an example where we use only satellite indicators alone. You could see the major driver for this prediction. You see NO2 being the most important variable, followed by NDVI and nightlight on the rest. And the result is is very encouraging, an accuracy of 2.8 mean absolute error. In the case of, for example, Botswana again, nightlight, we saw that NO2 was the major driver for Uganda. For the case of Botswana, nightlight and the rest, and we could also decompose the results and see how each variable or each indicator is contributing to the prediction. And the mean absolute error of 0.3 mean absolute error is very encouraging. Now for those countries in Group C, like I mentioned, where you have only annual GDP data, we developed two approaches, either to develop the model at the frequency the GDP comes, like annual GDP for the case of Somalia, or for the case of Afghanistan, where there is an urgent need for quarterly GDP data. We found a way to reconstruct quarterly GDP data from annual GDP data, and then develop from there, we train our model on it. But this is also a case where we combine traditional and non-traditional indicators to be able to have a very robust model for Afghanistan. Before bringing in, I want to say this, that we tried using traditional indicators alone to build the model, and the results weren't that encouraging. But the moment we brought in non-traditional indicators, satellite indicators, the results, the model improved a lot. And you could see the reason is because the major driver for this model in this case is nightlight coming from the satellite, and also we did what we call model explainability. Of course, you have to explain how the model works to the stakeholders. And, like I said before, the major driver for the model for Afghanistan is nightlight. here there is negative growth prediction for this quarter. And the reason is obvious, because nightlife is also having negative growth, and so on and so forth. And so we are using two methods to decompose. We are even able to not just do global decomposition, but we could decompose quarter by quarter and see what are the major drivers, how is the model behaving at every quarter, how does the model reach the conclusion that it reaches at every quarter. And that was very helpful for us to be able to, the economists to be able to also correlate the prediction of the model with what is happening on ground. Another method that also we try to use to certify that the model is doing the results are trustworthy, and the model is doing the right thing, is also to look at partial dependency plot of each variable or each indicator. Here, like I showed you, night light is the major driver for the model for Afghanistan, while EVR is the least driver, and it shows exactly in the partial dependency plot. Partial dependency plot, in a nutshell, is when you keep the other variables constant and you try to drive the model with one variable of interest, and you see how the variable behaves with the model. Here, you could see a more complex relationship with the model, nonlinear relationship with the model. It shows how this variable affects or contributes to the predictability power of the model. However, here is absolutely or very close to flat line. It shows when you have a flat relationship, in this case, it shows that this variable has little or no impact to the model. I'll quickly close here. So in conclusion, our conclusion number one is that our research showed that we can actually, with satellite indicators alone, we can shed light on economic activity. We can create reasonable, very good GDP nowcasting models for different countries, and it becomes better. It becomes better when there are some traditional macroeconomic indicators. The combination of the two can lead to a more robust quality models and accuracy. And this method is a method that is replicable. It can be replicated across different countries with similar circumstances. So our next step, what we are doing at the IMF, is now we are able to have this framework that is inclusive. So we want to be able to have this what we call the GDP nowcasting hub that desk economists can always go to and select any country of interest and be able to see the current GDP nowcast of the country, and also see how the results are reached at, and see the drivers of the result, and even look at the models, the machine learning models that are doing the job, and so on and so forth. So I'm going to stop here, and you can always reach us at IMF Big Data Center at imf.org for further questions. But thank you very much for listening.
Thank you very much, Ike. I know we are like 2 minutes away before going back. Can I ask, is Louis, Maria, so how are we doing in terms of time? Are we rushing back, or do we have a few minutes here?
We have exactly 2 minutes till we have to rejoin.
We only have 2 minutes.
Yeah.
So I'm happy to give up my wrap up time, because I'm going to probably wrap up also in the main session, because I also do the panel. There was a question that I didn't take. I don't know if that person wants to still ask a quick question or not. Is there any? Yeah, Osam, can you please give Osam the floor for a quick question, please, because we only have probably 1 minute now.
Osam, please go ahead and unmute yourself.
Yes. You can unmute yourself, Osam. Yeah, we cannot hear you, so I don't know if you're speaking.
Maybe turn on.
Perfect. No.
We can't hear you, Sam. So, well, you can write your questions in the chat if you wish. So why don't we maybe move back to the main session again? I want to just thank Abel, Gerd, Christian, Adi, and Ike for these excellent presentations. I believe they will all be made available to everyone. But thank you very much for your time and for this excellent work that you share with us. So I think we can move back now, right?
Yes, I posted the meeting link to the main meeting in the chat. Dear Hussam, I'm sorry about it.
Can we just leave this call or no? We need to move, join back.
Can I jump in now?
Oh, hi, Hussam. Hussam
Yeah,
is here.
thank you. Yeah, okay, I'm Hussam Khalifa from the Palestinian Central Bureau of Statistics. Thank you for the presenters. In fact, my question, I just wrote it regarding the staff and how they accepted the change towards using AI and machine learning and all these new techniques of data science in the production of official statistics. We in Palestine have launched an initiative here 4 years ago, and we start this modernization and using towards and moving towards using official the data science and the techniques in the production of official statistics. So we encountered some difficulties on top of that is the resistance to change. How about that resistance or how the staff accepted the change for the countries of the presenters? Thank you.
Thank you, Sam. I believe this is a great question, but it would take the full hour. So I suggest that we move to the main room, and maybe we will, I mean, all presenters can write in the chat their own views, but maybe we can also discuss this in the panel discussion. So why don't we move back and then we also discuss about this, Sam. Thank you for this question. So I'll see you back in the main room.